Hi, this is S. Lakshmanachari, working as Assistant Professor in the Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss the topic Input-Output Subsystem and Interfacing. So, in this topic, we are going to discuss the content Introduction to the I/O subsystem organization and the need of interfacing circuit using between the CPU and I/O devices. So that is the first content we are going to discuss, and then we will discuss the different types of peripheral devices. Then finally we will discuss the modes of I/O data transfer or I/O techniques. So these are the content we are going to discuss in this video. So let's start with the first content. So already we have seen in the previous class the definition of the computer. So computer is an electronic device. It is an electronic device and that can be programmed to accept the input, process it, and then it generates the results. So that is the definition of the computer. So if you see any basic computer organization, it consists of three primary subsystems or components. So that are CPU. So the first one is a CPU, Central Processing Unit. CPU means Central Processing Unit. So the CPU, it consists of again three internal functional parts that are ALU, Arithmetic and Logical Unit, then Control Unit, and the registers, internal registers. So this is a CPU. So the CPU, it performs many operations and it controls the entire computer system. Then the second one is the memory subsystem. Memory subsystem. Memory subsystem, it can be used to store the programs that can be executed by the CPU along with the program's data. And third one, I/O subsystem. I/O subsystem. So the I/O subsystem which allows the CPU to interact with the input or output devices. So if you look into the organization, basic computer organization, so it consists of total three subsystems. First one is the CPU, Central Processing Unit. Second one, Memory Unit. And third one is the input and output devices. So by combining, so all these subsystems function together as a single unit to deliver the desired output. Okay. So here the CPU, it treats the memory as homogeneous. So CPU, it treats the memory as homogeneous. So if you look into the memory, so the memory, it consists of different memory locations. So these are the memory structure. So how it will be. Okay. So it consists of multiple memory locations. Okay. So the memory location, every memory location, it is identified with a address. So using this address, we can read the data from the memory or we can write the data into the memory. So here with respect to the memory, so writing the data into a particular memory or reading the data from a particular memory location is happen in the similar way. So that's why the CPU treats the memory as a homogeneous. But this is not the case for the I/O devices. So I/O devices are very different. So the reading from the I/O device is different from the writing into the I/O device. Okay, and so here we are placing a interface circuit between the CPU, Central Processing Unit, and the I/O devices. So the interface circuits used between the CPU and the I/O device are in similar. Okay, so here each I/O device, it needs to connect to the computer systems. So we are interfacing many IO devices with the CPU. So whenever we are interfacing the different buses of the IO devices with the computer system, we need to connect to the all these buses. So already we have seen, so different basically three types of buses are there. One is the address bus, data bus, and the third one is the control bus. If you look into the address bus, so the address bus, it can be used to pass the address information to the peripheral device. Okay. Then the data bus. The data bus, it can be used to pass the data to and from the peripheral device. That means using the data bus, we can carry the data either from the input device, or we can also transfer the data to the output device. So which will the data bus which will carries the data information. So data. And the third one is a control bus. So which will carries the control signals. Which will carries the control signals to the peripheral device. Because with the peripheral devices, we can perform two types of operations. One is IO read, input or output read operation, and another one is input or output write operation. So read operation is nothing but we are reading the data from the input device. IO write is nothing but writing, sending the data to the IO device. So that is the difference between the IO read and IO write. So here you can see the IO subsystem organization and interfacing. So already we have seen the IO subsystem. So IO subsystem, it consists of multiple IO devices, which allows CPU to interact with the IO devices. So interfacing. So we are interfacing the IO devices with the CPU. Interfacing is nothing but connecting. So connecting the input or output devices with the CPU, so that the IO devices can communicate with the CPU. So here, if you look into the organization of these components, so we have a CPU, memory, and different IO subsystem. Okay. So whenever we are connecting any IO devices with the CPU, in between we are using a interface circuit. So here you can see the interface circuits. Okay. So in between the CPU and the IO device, we are using this interface circuit. We cannot connect directly. We cannot connect any IO devices directly with the CPU, because there is some operational characteristics differences are there between the CPU and the IO device. So due to that, we cannot connect any IO device directly with the CPU. So that's why in between the CPU and these IO devices, we are placing a one special component circuit that is called interface circuit. So this interface circuit will act as a converter, acts like a converter or translator. Okay. So that's why we are using the interface circuit in between the CPU and the IO device. So already we have seen some differences are there between the CPU and the IO device. So we will see the major differences between the IO device and the difference between the IO device and the CPU. Okay. So first we will see the need of the IO interface. Okay. So the IO interface, it provides a method. It provides a method for transferring information between the internal storage and external IO devices. So this IO interface is a method which facilitates transferring the information between internal storage device and the external IO devices. Peripherals connected to a computer need special communication links or interface for interfacing them with the central processing unit. So already we have seen in the previous one. So there is a difference between the central processing unit and IO device. So in order to resolve those differences, we are using a special communication links or interfaces between the CPU and the IO devices. So that special communication links are called interface circuit. So the purpose of the communication link or interface is to resolve the differences between the CPU and the IO devices. So this is a need of the IO interface circuit. So already we have seen the necessity of the using IO interface circuit. Now we will see the differences between the CPU and the IO devices. So the first difference is it is the signal values. Signal values. So the peripheral devices are the electromechanical and electromagnetic devices, whereas the CPU is an electronic device. So the signal values are different. So in order to match or convert the one form of signals values into the another form of signal values in between the CPU and IO device, we are using this uh, interface circuit. So that's why we are using a interface circuit between the CPU and the IO device. The second difference is the data transfer rate. Data transfer rate. So if you see the CPU and the IO device, so CPU will transfer the data at a faster rate, but the peripheral devices the data transfer rate is low, because if you consider any peripheral devices like some keyboard, so suppose with the keyboard we can transfer the data at a smaller rate. That means per second how many keys we can type, so that are very limited. Per second maximum we can type 3 or 4 characters. Similarly, if you take a printer, per second how many papers we can print, so that are limited in number. But the if you consider a CPU, it has to execute million instructions per second. That means CPU will execute the instructions at a faster rate. Okay, because the means there is a data transfer rate, there is a mismatch, there is a difference, there is a difference in data transfer rates of the CPU and IO devices. So in order to synchronize their data transfer rates of the CPU and IO device, in between we are using a special communication link that is nothing but the interface unit. So in order to synchronize the data transfer rates, we are using a interface circuit. That is the second difference. Coming to the third difference, that is nothing but the data codes and the formats. So the data codes and formats for the CPU and the IO devices are different, because if you see the peripheral devices, the data format is the byte or block. For the CPU and for CPU and the memory, the data format will be the word. Okay, so that's why in order to match their data formats between the CPU and IO devices, we are using a interface circuit. And the last but not least, the difference is it is operating modes of the peripheral devices. So peripheral devices operates in different modes, different modes from each other, and must be controlled as not to disturb the operation of the other peripherals connected to the CPU. So suppose we are connecting several IO devices with the CPU. So whenever we are connecting more than two IO devices, operation of one peripheral device, it should not disturb the operation of the other peripheral device. So these are all the some major differences that exists between the central processing unit and IO devices. In order to resolve those differences, we are using a special communication link or special communication component circuit between the CPU and IO devices. Okay, that is nothing but the interface circuit. So here you can see the example of the interface circuit. So this is an example of the interface circuit. So here it consists of this interface circuit. It consists of buffers, timing and control circuit, and different registers. It consists of port A register, port B register, control register, status register. So these are all the registers to store some data. And the buffer. In the buffer we can store some data. And timing and control circuit. So the timing and control control circuit will generate different timing and control signals in order to synchronize all the different modules inside the interface circuit. So the timing and control circuit having some inputs like CS. CS means chip selection. RS1 register selection. RS means register selection. We have two register selection inputs, RS1 and RS0. And two more inputs are there, that are read and write. Because we can perform read and write operations with the IO devices. So that's why we are there is a provision given for read and write. Okay. So here with using this chip selection pin CS and register selection pins, we can select the required register. So if you see this is a CS, RS1, RS0. So using that inputs, we can select the required register. Suppose if the CS is equal to 1, so CS is equal to 1 and RS1 is equal to 0, RS0 also 0. So in that case, port A register will be selected. Okay. So for chip selection should be always, it should be logic high. Okay. So suppose if the chip selection pin is equal to logic 0, then we cannot select any register. Okay. So to select the port A, the RS1 and RS0 should be 0, 0. In order to select the register B, the register selection values are 0, 1. In order to select the control register, the RS1 should be 1 and RS0 should be 0. Similarly, in order to select the status register, RS1 and RS0 both should be logic 1. So this is an example of the communication interface. And now coming to the different peripheral devices. So peripheral devices. So peripheral devices means the input or output devices that are connected to the computer. Okay. The input or output devices that are connected to the computer are called peripheral devices. So these devices are designed to read information into or out of the memory unit upon command from the CPU. Especially these peripheral devices are designed to read something data or write something data into the output devices. So these devices are called peripheral devices. So some of the examples given here. So keyboard. So the examples of peripheral devices are keyboard, display units, and printers. So these are some of the examples of the peripheral devices. So these peripheral devices are classified into mainly 3 types. So that are input peripherals, and output peripherals, and third one is the input output peripherals. So these are the main classification of the peripheral devices. So first one is the input peripherals. Input peripherals means the input devices which are connected to the computer. That is called input peripherals. That means these input peripherals which allows user input from the outside world. So that are called input peripherals. So these input peripherals will convert the input data into a pattern of electrical signals in binary. That binary signals are applied to the computer. Then the CPU will process that input data. Okay, so that are the input peripherals. So the examples of the input peripherals are keyboard, mouse, trackball, joystick, microphone, and webcam. So these are the examples of the input peripherals. And coming to the second type of peripherals, that are output peripherals. So output peripherals allows information output from the computer to the outside world. That are called output peripherals. So the examples of output peripherals are printer, monitor, plotter, projector, speaker, and headphones. So these are all the different output peripherals. And coming to the third type of the peripherals, that are input-output peripherals. That means it combines the properties of the input peripherals and the output peripherals. That means these input-output peripherals, it combines the operation of the input peripheral and output peripheral. So the examples of the input-output peripherals are the touch screen and the hard disk. So these are the classification of the different peripheral devices. And coming to the input devices, so interfacing of the input devices with the computer or CPU. So here you can see the input device and the tri-state buffers and enable logic. So already we have seen input device. So from using the input device, we will accept the data from the outside world. Then that input data we are giving to the CPU for further processing. So here, if you see the enable logic, this enable logic. So the inputs to the enable logic are address bus and the control bus. Okay. So for the correct values of the address bus and the control bus, the enable logic will generate a enable output. So this is a enable. Okay. So for the correct values of the address bus and control bus, the enable logic will generate an enable output. So that enable output will be applied to the tri-state buffer. Whenever the tri-state buffer it receives the enable input, then the tri-state buffers will be enabled, so that the data which is coming from the input device are passing through the buffers, and finally that inputted data will place in the data bus. From the data bus, the CPU will read that input data. So that is the process going. Okay. So if you see the enable logic, so here we have seen the block diagram, block of the enable logic. But if you look into the internal logic circuit, then it looks like here. So this is a circuit. This is a internal logic circuit. So this logic circuit will generate the enable output. Okay. So here let's assume the input device is mapped at an address this 11110000. This is the address the input device is mapped. So whenever the input device is having this address, then the data from the input device will be transferred to the CPU. That means, see here. So how the logic works here, you can see. So the address is so here the address is the starting from here A0, A1, A2, A3, A4, A5, A6, A7. So the address size is 8-bit here. Okay. So if you represent here the address as A7 1, A6 1, A5, A4, A3, A2, A1, A0. So these are the addresses. So A7, A6, A5, A4 that are connected to the input of the AND gate. So the output of the AND gate will be 1 because all inputs of the AND gate are 1. Similarly, the output of the OR gate, output of the NOR gate. So output of the NOR gate is a 1 because see here. So output, it is a NOR gate. Suppose if you consider OR gate, the output of the OR gate is a 0. But here bubble is there. Bubble means it indicates the inversion operation, NOT operation. So 0 becomes 1. And here 2 control signals are there. So these address lines are address bus, and this read and IO bar. These 2 signals it constitute the control bus. Okay. So this will determines the what type of operation it has to do. Read. So what type of operation we are doing with the input device? We are performing the read operation. Read. Okay. Read operation. So that's why the read signal is there. And IO bar. That means IO means input or output, and bar memory. Okay. So these are the IO is it is an active high signal. Memory M is it is an active low signal. Active low signal means it will be active only for the logic 0. Okay. So in order to perform the IO operation, this pin should be equal to 1. And in order to perform the read operation, this should be logic 1. So finally, the output of the AND gate will be logic 1 because the AND gate, this AND gate, it is having 4 inputs. That all inputs are logic 1. So output will be logic 1. So that means this is the output of the logic circuit, enable logic circuit. So now the E is equal to 1. E is equal to 1 means the buffers will be enabled so that the input data from the input device will pass through the buffers and given to the data bus which is connected to the CPU. Okay. So this is a process how we are interfacing the input devices with the CPU. And similarly, we can connect the output devices with the CPU. So once the CPU it processes the given input data, it generates a results, and that results will be given to the user using the output device. So these output devices, it performs the opposite operation of the input devices. So here if you see the interfacing of the output devices with the CPU, so we have a output device and the registers and enable logic. So once the CPU processes the input data, so let us assume this is a CPU. Okay. So CPU from the CPU we have a data bus which is connected to the this interface circuit. Okay. So here we are considering a register, but previously when we are interfacing the input devices with the CPU, we are considering a buffer, tri-state buffer. But here we are using a register. We are using a register because suppose if the CPU sends the data into the this register. Suppose if you consider a buffer, suppose if the CPU sends the data into the buffer, if the data present in the buffer is not read by the output device, means we will lose the data. So that's why we are not here. The previous buffers are replaced with registers. Okay. So the registers will be active whenever it receives a load signal, LD. LD means load the data. Load the data. So similar, same operation. So enable logic. So the enable logic will generate a load signal for the correct values of the address bus and the control bus. So same operation here. Here also you can see. Okay. So here also the output device, it is mapped at an address 11110000. This is the address of the output device mapped with the CPU. So if you consider same address, so similarly you will get the one same logic. Previously already we have seen. So whenever this enable logic circuit generates a load signal, then the registers are loaded with the data. Then the data present in the registers will be given to the output device. Okay. So this is a way of interfacing the output device. And coming to the third type, so already we have seen the peripherals are classified into input peripherals, output peripherals, and input-output peripherals. So already we have seen how to interface the input peripherals and output peripherals. Now it is a time to discuss the input-output peripherals. So we can also call the bidirectional devices. Okay. So here we are connected. That means we are combining the circuit of the input peripheral and the output peripheral. So this is for input peripheral circuit, and this is a circuit for the output peripherals. So we are combining both the circuits in order to design the input-output peripherals. Okay, and we are using the same logic circuit. Okay, so here combining the logic circuit, but that means here when we are interfacing the input devices, we are using the control signal only the read, because with the input devices we are performing only the read operation. That is with the input device. Suppose if you consider output devices, so with the output devices we can perform the operation write. We can perform the write operation only. So that's why we have mentioned only the read or write. But here in the input-output peripherals, we are using both read and write, because we are combining bidirectional input-output. That means that same device we can use as input and output. So when we are treating the device as an input, then we will perform the read operation. When we are treating the device as output device, then we are performing the write operation. So that's why here read signal and write signal both we have mentioned. Okay, so when we are performing a read operation, this read spin should be 1 and other write signal should be 0. Okay, so this is for read. Similarly, when we are performing write operation, this should be 1 and this should be 0. So that is for write. Okay. So in this way, we are interfacing input devices, output devices, and input-output devices with the CPU. And coming to the modes of I/O data transfer, modes of I/O data transfer. So the data transfer between the CPU and the I/O device, it takes place in several ways, that are programmed I/O. Second one is a interrupt initiated I/O, and the third one is a direct memory access. Shortly we can call DMA. So these are the three ways of transferring the information between the CPU and the I/O device. So we will see one by one. So first one is a programmed I/O. So in this type of programmed I/O, the data transfer will be initiated upon executing the instructions of the program. Okay. So so here the data transfer will be initiated by executing the instructions of the program. So that's why it is called programmed I/O, data transfer. So usually the program controls the data transfer to and from CPU and peripheral. So the program itself controls the data transfer between the CPU and the peripheral. So that's why it is called programmed I/O data transfer. Okay. So here you can understand with the diagram. So we have a CPU and the I/O devices. So the data will be transferred between the CPU and the I/O devices. So whenever the I/O device is ready to transfer the data, okay, then it sends it sends the data through the I/O bus to the interface. So already we have seen we are using a interface circuit between the CPU and the I/O device. Okay, already we have seen the necessity of using this interface circuit. So whenever the I/O device it places the data in the data bus, it will be given to the interface circuit. So the interface circuit it consists of the data register and status register F. Okay. So whatever the data is sent by the I/O device, that will be stored in the data register. And we have a status register which will indicates whether the data register it contains a valid data or not. So if the status register F is equal to 1, that means the data register it contains some data. Okay. So here in this the CPU it has to continuously monitor the status register F. Okay. So it has to continuously monitor the status register F. So if F is equal to 1, that indicates that there is a valid data present in the data register. Then the CPU can read the data using the data bus. Okay. So in this way, suppose if the status register F is equal to 0. So if the F is equal to 0, it indicates that the data register it doesn't contain any data. So the CPU has to wait until the status register F is equal to 1. So that means here in this programmed I/O data transfer, the CPU has to spend more time on checking the status register, that is a flag F. So that means the CPU's considerable amount of CPU's time will be wasted here. That is a drawback with this programmed I/O data transfer. Okay, so this is a programmed I/O data transfer. So in order to overcome the drawback, what we have seen, that is the CPU's time is wasting here by checking the status register continuously. Okay, it is a wastage of the CPU's time because the CPU has to execute some important programs, but instead of doing execution, it is spending more time on checking the status register F. If the status register F is not equal to 1, it has to wait until the status register F is equal to 1. So this is a drawback. So in order to overcome the drawback, we are going for the second type of data transfer, that is a interrupt initiated I/O data transfer. So in the programmed I/O, so already we have seen the drawback of the programmed I/O. So this problem is avoided or overcome with interrupt initiated I/O. So in this, when the interface determines that the peripheral is ready to transfer the data, then the interface circuit, it generates a interrupt. Okay. So after receiving the interrupt signal, the CPU stops the task. What the currently executing task, it will stop. Then it involve in the data transfer between the IO device and the CPU. After completion of the data transfer, again the CPU resumes its the previous task. So in this way, the data transfer will takes place in the interrupt initiated IO. So you can understood with a diagram. So IO device. So this is a IO device, and here it is a CPU. Microprocessor is nothing but it is a CPU. So whenever the IO device is ready to transfer the data, then it will send a interrupt signal to the interface circuit. So in between the IO device and the CPU, we are using some interface circuit. Okay. So this interface circuit will generate a interrupt signal. So whenever what is interrupt signal? Interrupt signal is it is a something which breaks the continuity of the processor. So whenever the CPU receives interrupt, then it can understand that the IO device is ready to transfer the data, so that the CPU, it stops its currently executing program, then it involve in the data transfer. After completion of the data transfer, again the CPU can resume its previous program execution. So this is a process of interrupt initiated IO. And the last type of data transfer is a DMA, direct memory access. So direct memory access, it can happen using the DMA controller. So this direct memory access, it is performed by using the DMA controller. What is DMA controller? DMA controller is a hardware device. It is a hardware device that allows an IO device to directly access the memory. What it will do? The DMA controller will allow an IO device to directly access the memory with less involvement of the CPU. That is called the DMA controller. So what is DMA? So DMA is a method. It is a method will allows an input or output device to transfer the data to the memory without involvement of the CPU. Okay. So without involvement of the CPU, that means we are bypassing the CPU in the process of in the data transfer. So the transfer of data between a fast storage device such as a magnetic disk and memory is often limited by speed of the CPU. So removing the CPU from the path, letting the peripheral device manages the data transfer between the IO device and the memory. Okay. So this transfer technique is called direct memory access. So direct memory access is nothing but the IO device can transfer the data to the memory without involvement of the CPU. So that is called direct memory access. So during this direct memory access, the CPU will be in ideal state. The CPU will be in ideal state. That means CPU it will not do any operation during this data transfer. And also the CPU, it doesn't have any control over the memory buses. Okay. So the DMA controller takes over the buses to manage the transfer directly between IO device and the memory. Okay. So here you can understand this entire scenario with this block diagram. So here these are the IO devices. DMA controller, CPU, and it is a memory. So we are considering a main memory, RAM, random access memory. So what will happen? So whenever the IO device is ready to transfer the data, then it will send a request signal to the DMA controller. It will send a request. Whenever the DMA controller it receives a DMA request signal, it sends a bus request signal to the CPU. Then the CPU will disables the buses, data bus, address bus, write, read signal. So all its buses will be disabled, and the buses of the CPU will be granted to the DMA controller. So it will be given with the BG signal. BG. So BG means bus grant signal. So that means whenever the BG is equal to 1, it indicates that the CPU has disabled its buses, and the control of the CPU's bus will be handed over to the DMA controller. Okay. So now the DMA controller will take over the control of the all these data bus, address bus, write signal, and read signal. Okay. Then this this DMA controller will involves the data transfer. That means the DMA controller will send a DMA acknowledgement to the IO device. So whenever the IO device it receives a DMA acknowledgement, then the IO device will start data transfer. So the IO devices will start the data transfer. That means the data from the IO device will send through the DMA controller to the memory. So it will in this way. So from the IO device through the DMA controller, it will be sent to the memory. Whenever the data transfer completed, then the DMA controller will send a interrupt signal. The DMA controller will send a interrupt signal. Whenever the interrupt signal is received by the CPU, then it disables the bus grant signal. It disables bus grant. So disables bus grant means so the CPU will take over the control of this. So CPU will take the control of data bus, address bus, write, read. So that means here whenever the bus grant signal is disabled, then the DMS controller data bus, address bus, write, and read buses will be removed. That means DMA controller will releases the buses so that the CPU can take over the control of all these buses. Okay. So this is a process of how we can transfer the data from IO devices to the memory without involvement of the CPU. So in this way, we can transfer large amount of data from the IO device to the memory. Okay. So in this class we have seen IO subsystem organization and interfacing. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.